In this slide, we will talk about the multiple roots because they can exist and they can be a problem for the numerical approach. A multiple root corresponds to a point where a function is tangent to x-axis. And here you can see some examples. A double root, for instance. Of course, in the function, we can show it first. For example, here, x minus 1 times x minus 1 gives us a double root because we have two x values as 1. And this double root is represented in a graph, as you can see over here. So it basically goes through the x-axis in a tangent. So it is just touching at one point, and so that the x-axis is a tangent for the curve at this point. That means we have a double root here. Another case is triple root, in that we have three multiplication of the same, for example, x minus 1. And here again it goes tangent, the x-axis is tangent to the curve, but the sign is changing. So basically it comes from top, for instance, and goes and tangent here and goes down. Here the sign wasn't changed. It was coming up and coming down again at the same region. Here though, the regions are different after and before the root, you can see. So here this is only one because it is not a tangent here, but here it's a tangent. So a quadruple root also can exist, and here again we have a tangent with sign the same. We have the same region before and after the root, but you can see the difference of the double and quadruple. This is just touching and going down quickly, but this is maybe going more smoothly at the x-axis, more straight. So from these observations, we see that actually if we are just touching the x-axis in a tangent way and going down again, then we can have double roots, quadruple roots, or 6 roots. So we will have even roots in this case. The other case is if we are tangent again to the x-axis, but the sign is changing, the region is changing after and before the root, then it means we will have triple root. That means we will have odd roots. The odd roots are like triple or 5 or 7. So these two classifications are important to understand how we can deal with the multiple roots. The numerical methods have some issues for finding the multiple roots, and we will talk about them. In this slide, we will talk the first two issues, and in the next slide, we will talk about the third issue. There are 3 issues. The first issue is that the bracketing methods are not usable because the function does not change sign at even multiple roots. So for the even cases, even if we have even multiple roots, the bracketing methods will not be usable because there is no sign change. For the bracketing lower and upper bounds, the sign change was important for the prediction of the new value, and this is the reason of not using or not being usable for the bracketing methods. For this reason, we only use open methods for the multiple root calculations. The second issue is for the open methods, because now we can only use them, not only fx but also the derivative of fx, f prime x, can go to 0 at the root. Actually goes to 0. And going 0 is a problem, especially for Newton-Raphson and as well as for second method. The derivative is at the denominator part of the ratio at the bottom, and if it is 0, it gives an infinite value. So we don't want it, and the prediction will diverge in that case. And because of this reason, these methods can lead to a problem of dividing by 0. So the solution to this issue can be, for example, this. The study in 1978, this study showed that theoretically the function value will always reach 0 before the derivative value. So if you realize that the function value is going to 0, then we have to be careful. We will think that, okay, soon enough the derivative will go to 0 as well. And therefore, if a 0 check for fx is done, the computation can be terminated before the derivative reaches 0. That's why we can simply use this idea of just checking fx. If it is 0, then we just stop it, terminate the computation, because soon enough the derivative will reach 0 as well. Once we have this modification, we may use the open methods without having this issue of having 0 denominator. The third issue for the numerical methods for finding multiple roots is that the Newton-Raphson and second methods are linearly rather than quadratically convergent for multiple roots. So this linear convergence can be a problem. That's why we can have a modification to have a quadratic convergence. And we can do this way. We can say that our numerical method, which is basically Newton-Raphson, was this, if you remember, fxi divided by f derivative xi. This was our Newton-Raphson method. So instead of this, we can simply add and actually add value m, a parameter, let's say, or a variable, and this m represents the number of the root, whether it is double, the multiple root number actually, double, triple, etc. And m is 2 for a double root, and m is 3 for a triple root, etc. This can continue this way. So with this modification, we can have at least a quadratic convergence. But still, there is an issue for this modification. We don't know the number of roots beforehand to use this multiplicity constant. What we mean is that, so we have the polynomial and we want to find the roots from the beginning, and we don't know if there is a multiple root or not. So if we don't know if we have multiple roots, how can we decide this? That's a big question. That's why there is another alternative, and we define a new function ux for this purpose, and we say that ux is simply a ratio of fx and f prime x. And that's why we can simply use the Newton-Raphson method using this ux and derivative of that. So the derivative of it becomes u prime x is equivalent to, we have the chain rule here to have the derivative of these. It is f prime x minus fx f double prime x, the second derivative, divided by f prime, the first derivative, x, and its square. So this is the derivative, and simply we use the Newton-Raphson formula with this ux value. So instead of using, so if you remember the actual formula, it was this. So instead of this, we change fxi with uxi. Then we say xi plus 1 equals xi, and instead of f we use uxi and u prime xi. So then we are using this here, substituting here, and this one to here. If we substitute them, then xi plus 1 equals xi minus f xi. If we substitute and organize these, fxi f prime xi divided by the f prime xi square times, not times, minus fxi and f prime xi. So you can see here we have a formulation now for Newton-Raphson with this modification. Modified Newton-Raphson for the finding of multiple roots. You can simply use this for finding it. We can do the same for second method, and we can have a modified second in a similar way. And in that scenario, if you remember, our function was, first of all, xi plus 1 was equal to xi minus fxi times the backward difference of the derivative, backward difference approximation of the derivative, fxi minus 1 minus fxi, this result. And if we again substitute this here, fxi is this, actually let's say uxi, and the uxi formulation, simply these functions, again this, and we can use the same here for fxi minus 1. Eventually, when we organize these, we will have xi plus 1 is equivalent, actually we are just substituting uxi here rather than this, and so the formulation becomes uxi xi minus 1 minus xi divided by uxi minus 1 minus uxi. And now we can substitute uxi and uxi minus 1 by these, simply here as well, and here too for uxi minus 1. And this function is the modified second function, so we can have this function as well. In summary, for Newton-Raphson we have a modification with this function. Similarly, for modified second we have a modification with this function as well by substituting this instead of f values. Then we can have these modified results. Let's check an example about this in the next slide.